Hi guys. So you just watched, hopefully, the video where I talked about translations up, down, left, and right. Those are all rigid transformations. We talked about how if you're moving left and right, that's something that's inside the parentheses with the X. It goes opposite of where you think it's going to go. And then if you're moving something up and down, that's out on the end. And that goes the same way that you think it's going to go. So in the first two examples, we're just describing different transformations. So I am looking at the first one, an absolute value. I have drawn in this absolute value parent function, and I'm just going to move it left 3 and down 2. So if I take any point on here, if I go 1, 2, 3 to the left, down 2, that's my new vertex. Take the next point to the right. 1, 2, 3, 1, 2. The next point. 1, 2, 3, 1, 2. And then if I go the other way, so this one will go 1, 2, 3, 1, 2, and then 1, 2, 3, 1, 2. So here is my new function. The new vertex is -3, -2. And the new function, now this is something that's a little bit new for us right now, but you have talked about in Algebra 1. The parent function is the absolute value of x. Now, because I moved it left 3, that is a horizontal shift, and that goes inside these brackets because that's technically like inside parentheses. So it's left, which means I'm opposite of that, so that's +3. Because you're thinking of like minus a -3. And then since it's going down 2 on the outside, I subtract 2. So my new function is f of x equals the absolute value of x plus 3 minus 2. All right, so my next one is a quadratic, and it's just being translated up 6. So I'm going to take each point and count up 6. Now it actually even ends up falling off the graph, but you get the picture. Now the vertex of this one is 0, 6. And the new function, it was originally x squared. It didn't move left or right, so I don't need to put parentheses inside there. And it moved up 6. So it's f of x equals x squared plus 6. So something that's really important when it moves left and right, you really need to think about what grouping symbols are around the x. And if you need parentheses, or if you need it in the square root, if you need it inside that absolute value sign, things like that. So let's look down at numbers 5 and 6. Now I've already written in the parent function here, just in the interest of saving time in this video, but if you want to write it down, you honestly should pause this video real quick and get it down on your paper. So I've got the square root of x plus 4 minus 2. So the parent function here is the square root of x. So here is the table that goes with the square root of x. So now I notice that on the inside, I've got +4, which means whatever happens to my x's, each one is subtracting 4. So that's going to go left. On the outside, I have -2. So that means it's going to go down 2. So when I write my y's, I'm going to take my original y's and I'm going to subtract 2 from each of them. So let's see how this looks. 0 minus 4 is -4. 1 minus 4, -3. 4 minus 4 is 0. 9 minus 4 is 5. 16 minus 4 is 11. Nope, 12. All right, so then 0. Now for the y's, I'm subtracting 2. So 0 minus 2 is -2. 1 minus 2 is -1. 2 minus 2 is 0. 3 minus 2 is 1. 4 minus 2 is 2. So now I take each of these points and I plot them. So -4, -2. -3, -1, 0, 0, 5, 1, and I can't fit that last point. So here is my graph. So I noticed that it moved to the left. If I look at the starting point, that's a really great way to make sure that it makes sense. So my starting point was 0, 0, and that point moved to the left 4 and down 2, which makes sense because that's what I described here. I can look at other points like this one right here was 1, 1. If I count 1, 2, 3, 4, and then down 2, I get to a point that's on my new graph. And then this one, 1, 2, 3, 4, down 2, that's also on my graph. So that's just a way to check. The tables are really helpful in doing this. Again, the tables are going to be so important as we go into more than just these transformations. So for number 6, I have the cube root of x minus 3 plus 1. So I've already written down my cube root function because that's my parent function. And I notice that since minus 3 is on the inside, that means I'm going right 3. And plus 1 is on the outside, so I'm going up 1. So my x values, I'm going to add 3 to all of them. My y values, I'm going to add 1 to all of them. Once again, keep in mind, whatever's happening on the inside, you're actually doing the opposite of that to the x value. So negative 27 plus 3 is negative 24. Negative 8 plus 3 is negative 5. Negative 1 plus 3 is 2. 0 plus 3 is 3. 1 plus 3 is 4. 8 plus 3 is 11. 27 plus 3 is 30. On the other side, I'm adding 1 to all of them. So negative 3 plus 1 is negative 2. Negative 2 plus 1 is negative 1. Negative 1 plus 1 is 0. 0 plus 1 is 1. 1 plus 1 is 2. 2 plus 1 is 3. And 3 plus 1 is 4. So let's plot these on the graph. I can't fit the first one, but the next one, negative 5, negative 1. 2, 0. 3. 3, 1. Oh, I did negative 2. 2, 0. 3, 1. 4, 2. And I can't really fit the rest of it, but I'll just draw the line going in that direction. It's going to be somewhere up there. So notice I made a mistake while I was doing this and I plotted negative 2, 0. But you could tell I definitely knew I was doing something wrong because one thing to keep in mind is that rigid transformations, by definition, they do not change the shape of the graph. So I noticed that something was going to be weird about the shape of the graph if I had that point there. So once I got here, I recognized that this one should go like up 1 over 1 from that point if I'm going to have the same type of shape. And that then made sense to me. So just because you might like have done one of your math facts wrong, like, negative 1 plus 3, maybe you got the wrong answer. That doesn't mean you just have to blindly follow those points. Go back, check it out, make sure your shape is the exact same as the one that you started with your parent function. If all you're doing is moving the graph, the graph should look generally the same. All right, I have 2 more to go. These ones are just a little bit trickier because they're using log functions, and this is brand new information. So I didn't write the parent functions because I want to remind you of how to go about writing those parent functions. So the first one I have is log base 2 of x. That is my parent function. Now, some people like to start with an exponential function and transform it into a log function. That's fine. So I could go down here and think about 2 to the x and then flip it to make log base 2 of x. So 2 to the x, I have been doing negative 1, 0, 1, and that would be 1 over 2, 1, and 2. So if I take this information and bring it back up here, I can say x and y is going to be 1 over 2, 1, 2, negative 1, 0, 1. In general, this is most of your comfort zone. So if you start with this and just flip-flop it to make your parent function for log, that is fine. And I know a lot of people are more comfortable doing that. I just want to offer that as a strategy. If you're more comfortable, so this other function is log base 3 of x. So if you're more comfortable just looking at it like this, log base 3 of x, and you can remember x, y, and you have 1 over base 1 and then base, negative 1, 0, 1. That's also fine. So this is more of like, in my opinion, it's kind of like a memorization tactic. This is more of like an understanding where you're starting with something that's comfortable to you and then evolving it based on what you know of inverse functions. So either way, each of these are fine ways to get to the parent function, and these are your parent functions for these graphs. So I'm going to quickly graph those. 1/2 comma negative 1, 1 comma 0, 2 comma 1, and I'll make my nice curve. I also know that one of them would be 4 comma 2, because if I kept going, it would be 4 and 2. So here is my log. Now for my other one, I have 1/3 negative 1, 1, 0, and 3 comma 1. Now keep in mind, no log function should pass over your x-axis when it's in its parent function form. So that's something that really keep in mind. Remember, that's called an asymptote. So if I'm going to start this out, this has an asymptote right here. And so does this one. That's a line that it goes really, really close to and never actually touches. All right, so now I'm going to make these transformations. Look at this. This plus 5 is on the inside. So that means it's affecting the x's and it's moving left. So opposite of what you think, left 5. So I'm going to take my x values and I'm going to subtract 5 from them. There is nothing happening on the outside, so the y's actually stay the same. All right, so 1/2 minus 1. minus 5 is going to be negative 4.5. 1 minus 5 is going to be negative 4. And 2 minus 5 is going to be negative 3. One thing to also keep in mind, notice this had an asymptote here. When you shift the function left or right, since this is a vertical asymptote, that also shifts with it. So this asymptote was at x equals 0. Now it's going to be at x equals negative 5. It's also going to shift left 5. So here is my new asymptote, which is definitely going to help you graphing log functions once they have your transformations on them. So I have negative 4.5 comma negative 1, negative 4 comma 0, negative 3 comma 1. Now something else I could do, see this point here, I could count 1, 2, 3, 4, 5, and there's another point for me. So here is my transformed function. Really just make sure you're paying attention to where that asymptote is. I would honestly draw that dotted line every single time. It should not cross that line. So for my next one, I've got plus 1 on the outside. So on the outside, that means it's moving up 1. So I'm going to take my x's are going to stay the same. And my y's are going to add 1 to them. So this is going to be 0, 1, 2. So I have 1/3 comma 0, 1 comma 1, and 3 comma 2. Notice I didn't move left or right, so I still have that same asymptote here at x equals 0. This one just moved up 1. And there you have it. That is your note section for rigid transformations, specifically horizontal and vertical shifts.